next up, we can welcome to the stage Madkour, who is here to talk about expressive range analysis.
Hello. I feel very professional with the mic in my hand.
Yeah, there we
Uh,
go.
all right, now we have the slides. Hi, everybody. My name is Abdelrahman Madkour. I go by my last name, Madkour, pronouns he, him. And I'm a PhD student at Northeastern. I research PCG and trying to come up with tools for controlling and developing PCG. And today I'm going to talk to you about some work I've been doing and some work that's been happening in the ivory towers of academia about controlling and sort of analyzing content generators. This talk is going to be split into sort of two parts. The first part is going to be sort of the high level ideas, things that you could sort of maybe implement in your own games and your own generators. And the second part is sort of how these ideas tie into the specific system that I worked on, and sort of demoing that system a bit. I have a GIF of it. I don't actually have like a deep demo of the system running. But if you want the system, you can at me. I'll have my email, my Twitter handle at the end of the last slide, and I'll be happy to share that with you. All right. So first of all, controversial hot take: PCG is hard. So again, in the ivory towers of academia, a lot of people are spend a lot of time thinking about how to come up with content generators that are diverse and that generate, playable levels or playable content. And there's a lot of effort from sort of the computational perspective of like how do we get computers to be creative and do all these things that are really difficult to do, and sometimes humans have a hard time explaining why certain things work. And one problem that is still an open research problem is evaluation. How do we, when we develop these systems using all these fancy AI techniques, how do we make sure that we've made something that's worthwhile? And to that end, expressive range analysis sort of was formed. As far as I'm aware, this is the first time it was sort of visible, at least in academic circles. It was this paper by Smith and Whitehead. And the idea is, if you have a generator, in this case, they were working with Mario level generators. If you want to see, how well it's doing, have it spit out a bunch of things. In this case, Mario levels. Academic PCG researchers love Mario, so you have it, generate a bunch of Mario levels, and then you have some sort of function that evaluates your content. We're not going to go into the specifics of these functions right now because they're heavily game dependent, and we'll talk a little bit more about what these metrics, what we referring to as metrics, are, and maybe ways to think about coming up with them. But if you have these metrics in this specific plot, linearity and leniency, again, don't worry about what those exactly mean, but some sort of score from 0 to 1 of like loosely how linear your level is, or how lenient your level is, you can plot it in a 2D plot, like this heat map, where the darker the cell is, the less in that specific range of linearity and leniency your generator generates, right? So this sort of shows you how expressive your generator is. And the range of its expressivity, and then you can analyze it. Therefore, expressive range analysis. This is like ubiquitous in PCG research, so you might have seen this before, and has been used as a way of evaluating PCG. A lot of PCG systems, a lot of papers will be like, we've developed so and so, and then this is the expressive range analysis of our generator, and sort of preempting a little bit. Couple of future slides. The main crux or the main idea behind the work that I was doing and worked on is sort of how can we use this specific thing to guide and control PC content generators, right? So we have this way of analyzing them. How do we directly use it to control it? So let's first talk about metrics. There were supposed to be some animations here, but it's fine. So metrics, like I mentioned earlier, they're heavily game dependent. So I don't know if you're working on Mario levels, there's some papers on like some of the metrics that might be of interest, but there are, as you would expect, proxies of quality. you're not going to get a magic function that tells you level good, right? But some ideas that you might want to be thinking about. So I've been working on dungeon levels, things that to consider, like how many paths there are to completion, branching factors, number of enemies, how many random paths there are. I'm not a game designer. I'm sure you people are going to be able to come up with things that are much more useful to you than I can. But if you have ideas about sort of how to come up with these metrics, I'm very interested in sort of thinking about ways to facilitate metric development and ways in which that could be, we can develop tools to help you do that. So if you have ideas about that, at me. I'll give my socials the last slide. But a system that currently exists that lets you do that, and there is a GIF here that unfortunately is not currently working, but you can sort of look it up hopefully after this talk or after Roguelike Celebration. I don't want to have someone else talk be interrupted. But basically, Danish or Danish, I'm not sure if this is Arabic or some other language that uses Arabic script. Context, I'm Egyptian. So if this is Arabic and I'm mispronouncing it, then I have failed my heritage. But Danish is the system cooked up by Mike Cook, who you might know as the person behind Angelina, the AI video game designer, and also one of the co-founders of ProcJam. Very influential researcher. I highly recommend you check out his work if you're interested in reading papers about PCG. Also, super nice guy, so reach out to him if you want to. So Danish lets you visualize your generators and using expressive range analysis. The website has the GIF that I took this out of, but basically you can sort of look at each specific point in the expressive range analysis and see the level that corresponds to the point in the plot. And Danish lets you sort of visualize it. And this is sort of a cellular automata example. And Danish is, I think, a Unity. Yeah, it is a Unity plugin, so you can sort of use it now in whatever Unity project you're working on. This is a sales pitch for Mike Cook's tool. So that's one way of visualizing it. The other thing to think about, or I wanted to think about, and maybe you want to think about, is how to adjust the generator. Right. So now you have this thing to tell you what your generator looks like. How do you adjust it? So one thing to do is just if you have a very manual level, manual PCG algorithm, you can continue to adjust your variables, adjust your algorithm until you figure out what regions of the expressive range you're hitting and where you want to be, and you can continue to do that because that's something you could do if you want. If that's your only option, that's one thing you can do. The other thing to do, which I think is the thing that came to mind for me, was parameterize your generator, and it's also something that came to mind with Mike Cook. I say it's my idea, but I had a bunch of these ideas, and I'm like, oh wow, I am so clever for figuring this out. And then I read Mike Cook's paper, and I'm like, oh, Mike Cook beat me to it. But there's something subtle that we add that I'll talk about later on that I did work on. But yeah, parameterize your generator. For cellular automata, you can have birth limits, depth limits, number of iterations. It depends on what kind of PCG technique you're using. But if you have some sort of parameters, then obviously adjusting those knobs will let you adjust the generative space. For grammars, which is what we're going to talk about in more details later on, you can control which rules are applied, which are Joris Dorman's recipes. If you're familiar with grammars, you know that there are a bunch of rules that you can sort of apply or can be applied. You can control the expressive range of your grammar by manually saying which rules apply. Like I'm going to apply this rule and this rule and this rule and this rule, and that's what Joris Dorman's calls recipes. Or you can weigh the grammar rules and adjust those weights, and we will talk about that later on. Danish also lets you do this, and this was also a GIF. So there's a bunch of slides that you can adjust to control your cellular automata, and then it sort of shows you how that affects your expressive range analysis. And it also has some mechanisms for sort of doing some local search so that you can optimize your parameters to find a specific area in the expressive range that you want. But crucially, and this is crucial for me, so that's the reason why I got my paper published, it does not allow you to select an expressive range, a portion of your expressive range, and then move your generator towards it. It just lets you sort of optimize for specific metrics. So you might be looking at this and cool, dude, but adjusting is hard. This seems like a lot of manual labor, the kind of thing that we would use, we would outsource to the global south. I mean, use AI for. And so naturally, you might be thinking, can I use AI for this? And the answer is, of course, yes. This is a very clear and cut optimization problem. And so you can brute force it if your parameters are the parameter space is small enough. If you don't have that many parameters, you can just brute force it if you want. You can use genetic algorithm. You can do hill climbing or some gradient descent, convex optimization stuff if you're into that. You can do all of these kinds of things, but then which would work. But in my mind, that would sort of like being the same. You sort of go back to this problem of, okay, now you're super dependent on coming up with an appropriate way to optimize these things. And it sort of gets it's sort of basically the same problem that PCG researchers are doing. It doesn't give you a direct way of controlling the generative space. It's still hidden in the details of the hill climbing or the genetic algorithm or whatever. It's hidden in the way that you search the space. Another way to do it is to learn from examples. And that's sort of the approach that we're going to talk a little bit more about. Where basically you figure out which parameterizations sort of are the things that you want in the expressive range analysis, and say, hey, these parameterizations are good. Let's try to do more of these, right? And so you are learning from examples, and we'll talk about that in the context of grammars in the second half of the talk. So part one, takeaways. Expressive range analysis is a useful tool for visualizing your generator. You can use it to guide your generator design process. So when you're coming up with your generator, you can use it as sort of like a thing to anchor or guide your design process. You can parameterize your generator so that you can sort of easily adjust it, so that you can sort of try to see how changing your parameter maps out to changing your generative space, or the design space of your generator. And you can use AI to automatically adjust these parameters towards a specific area or specific metric that you want to optimize. So that is part one. And research shows this was supposed to be supposed to be an animation. That I should have some cat gifs here, take a bit of a break, let you sort of digest this information a bit before I go into the next stuff. But since there are no animations, I'm just going to go into the next slide. So grammars review. So grammars, real quick, are this computational model that was born out of linguistics by Daddy Noam Chomsky. The daddy of all linguistics. He came up with these formal systems for describing natural language, and people in the natural language processing community realize it's not actually. Natural language is more complicated than what these computational models can actually represent, but they tend out to be useful in a bunch of different areas, including content generation. So that the idea is that there are string rewriting systems, or rewriting systems in general, where you have like a start thing, which like the start sentence XYZ, and you have something called terminals and non-terminals. And terminals, as the name would suggest, are things that are terminal, which means they are the end things. Which we'll expand on a little bit more. Non-terminals are the exact opposite. So what that amounts to is that in your rules, the left-hand side of each rule has to be a non-terminal, and the right-hand side can include a mixture of terminals and non-terminals. And what you do as the part of the grammar or the rewriting system is that you look at your start sentence or your start state, you see the non-terminals, you look at your rules, you figure out a rule that applies, and then you replace that, you replace your X in this XYZ example, for example, with AY or B, replace Y with B, X or AZ, and replace Z with C, right? This is a very dummy, basic grammar that is not useful at all, but hopefully gets the point across. And generative grammars are used everywhere. You might have heard of speed tree, which is like one of the industry standards for generating trees. City Engine is also a popular proprietary software for generating buildings and cities. And these software are pretty complicated, pretty sophisticated, but the underlying technology or the underlying generative system that they use is based off of grammars. One key thing to note, there we go, is that they are specific grammars for the specific thing that they're trying to specifically generate, right? So City Engine uses a very specific shape grammar for generating buildings. speed tree uses L systems that are like designed to generate trees. So, they're cool software for what they're used for, but, coming up with your own grammar for whatever purpose you need, like say you want to generate some mechs or something, or guns, you can't really use these software for it. You can't use these grammars. And so the usability tools built on top of it sort of depends on the fact that it's a specific grammar. And the reason for that, again, is grammars is hard. It's difficult, much like a lot of the much like this is the problem that comes that you run into again and again, is that the input to a lot of your generators does not necessarily map out to not directly map out to your output. So if with grammars, your rules, your terminals, the design of your grammars, it's very difficult to map that out in your head towards like what you want in the expressive range or what you want in your generator, right? And so some research is trying to address this. This paper in particular is trying to sort of is proposing a way for us to debug grammars, much like you would debug code. And the idea is that you have this metric that sort of tries to measure how a given rule changes the level or whatever thing you're trying to generate. If you're more interested in that line of work, check this paper out. They are, I think they have some code on GitHub called Ludo Lite that you might want to check out. But the idea, is that it helps you sort of come up with these grammars by debugging them. So that's a cool line of work. It's kind of tangential or orthogonal to what we're going to talk about today, because it helps you come up with a grammar. It doesn't necessarily help you control it or sort of manage its expressive range explicitly. It's basically trying to measures the effect of a specific rule using their metrics. It doesn't directly use expressive range analysis. So background for my system, the system that I worked on, this is Joris Dorman's. He's cool. He made the game on Explorer or worked on it. They're currently working on Explorer 2. And if you look at the Steam reviews for this game, a lot of people compliment its P2C system, which is understandable given that he got his PhD working on some of the systems underlying the level generation for Unexplored. And one key paper that I'm going to sort of base the rest of the talk on is this paper, which was proposing how I was sort of trying to discuss ways of generating Zelda levels. And the way that Joris Dorman sort of proposed it is that you can split the generation process into multiple phases. Specifically in the paper, though later on he mentioned like, oh, actually you need way more than two. But in the paper, he mentions two, mission generation and space generation. Mission being sort of the things that you do to finish the level, and space generation being the space where these sort of tasks are done. And these two things can be generated in either order. Sometimes it makes more sense to do space. Sometimes it makes more sense to do missions. For my work, I sort of focused on mission generation. And for that, Dorman's proposed use of graph grammars, which are grammars that operate on, yes, you guessed it, graphs. And which sort of ties in perfectly with the causal graph talk. Well, not perfectly, but somewhat well with the causal graph talk, because, hey, graphs. Graphs are sort of these things that, these computational representation that are really useful and like are used everywhere. That's redundant. But the idea is that you have, these nodes that represent things, and you have edges that represent relationships between things. And in the examples going forward, you can think of the nodes as rooms and the edges as sort of doors or paths to the rooms. And this is an example of a graph grammar. And similar to string rewriting grammars, graph grammars are rewriting systems. But instead of operating with strings, you're operating with graphs, right? So you have an initial graph, and you have rules, and you have terminals and non-terminals. The rules, you basically replace. You look at your graph, you try to find a subgraph of that graph that matches one of your rules, and then you replace that subgraph with the thing on the right-hand side. And the way you do that is that you actually, we're not going to talk about that because that's a little complicated, but there's ways to do it if you're interested. There's Dorman's papers, there's my paper, there's the PCG book. At me, I'm happy to explain it. We don't have much time, so I'm going to breeze through that. But that's what graph grammars are. So how do we control them with expressive range analysis? So the idea of controlling with expressive range analysis is how about we control them via examples. So we can think about the generative space of the graph. Okay, this is fancy talk for basically saying, let's look at the expressive range of the initial grammar. So suppose that you already have a graph grammar, and we'll talk about why you would suppose that you have that. But suppose you have a graph grammar, generate a bunch of stuff, and then sort of parameterize that generation process with some form of probability parameters in two ways. One, parameterize which right-hand side of a rule. So as you can see here, there's like multiple right-hand sides of that rule. So what that means is when you see this left-hand side, when you try to replace that left-hand side, you have two options to replace it with. You can replace it with, let's pick the first example, ST here, right? You can replace it with STT or STTTT. So there's two forms of stochasticity, which right-hand side that gets picked. And then there's the other level of stochasticity, which is which rules that are, out of all the rules that you can sort of apply, which ones do you pick, right? And so if we can parameterize that, can you use that to shift the distribution towards that of the desirable examples, that of the places in the region that you want? And so the way you do that, or the way that I propose we do that, is that you can sort of keep track of when you're generating your levels, you can keep track of what the grammar did, right? So this is, if you can sort of think of this, if you're familiar with grammars, as a quasi-equivalent to parse trees. Essentially, you're keeping track of what rules were applied and when. So with a graph, you have this what we call just a generation chain. It's a fancy name for something. It's relatively straightforward. You keep track of basically, again, which rules were applied when they were applicable, and which right-hand side was applied when applicable, right? And that way you have sort of something to keep track of, such that you can compute a weight or a parameter for the rule, both on the right-hand side and sort of when it was applicable. And my system, unfortunately, the GIF doesn't work. Let me see if I can do this real quick. Okay, can we switch to my screen sharing? Because I think this is important. Okay, yep, thank you. Okay, so I hope you can see the system. So the system lets you sort of analyze the graph, or sort of the graph grammar, and the graph grammar by looking at things, and then seeing the corresponding graph, and then it lets you select a region, train on it, and then see the resulting thing. And that's my system. Short, hopefully sweet, and then let's switch back, please. Sorry. Yep, thank you. Nope. Yep, thank you. All right, so limitations of that system. Technically, there's like, okay, well, first of all, we did not solve world wars, unfortunately. Is something that we all strive for. It was a stock photo of this template that I was using for the slideshow, and it was too funny not to include. I apologize. So technical limitations. The learning mechanism isn't perfect, so it's basically just weighing sort of what rules were applied in the examples that you selected. And what rules were not, and sort of weighing that and adjusting the distribution of or adjusting the generative space or the expressive range of your system, of your generator, based off of that. It could do better because it's not really trying to explicitly account for the specific region that you're selecting. It's sort of just looking at the examples that the grammar happens to generate in that region. So there could be more work to maybe optimize that. We can still have oatmeal. So we don't really avoid the 1,000 oats problem. Nothing inherently prevents oats. That still comes from the underlying grammar and sort of your metrics. Speaking of which, metrics that we used were based off of other work, and I don't want to begrudge other people's work, but as a field, metrics that we come up with are relatively sort of not nuanced enough to capture design nuances that you may care about, and therefore this is sort of an ongoing research question of like, how do we come up with metrics that are useful? And another thing is that this system sort of requires an established grammar. In this work, we use the grammar that Dom has proposed in this paper, but for whatever you would need, you'd still need to come up with a grammar. So it doesn't solve that problem of coming up with the grammars, which is something that I'm working on currently. So I guess look forward to that if you care about anything I said. So you would still need a grammar to sort of do that, but hopefully it'll help you sort of control a grammar that you have or control the generative space of your grammar. And that's how to use expressive range analysis to control your generators with specifically applied to a grammar-based generator. I am at A3 Madkour on all the socials. I don't change my handle at all because I'm basic. And this is my email, my Northeastern email. If any of this is interesting to you, if you want to talk about metrics, if you want to talk about PCG, if you want to ask me how I'm doing, please feel free to reach out, and I'll be happy to take any questions. Thank you so much for your time.
Thank you. Yeah, fantastic. I appreciate, too, the on-the-fly attempting to balance the, getting into the complexity, but also trying to use the time. It's a hard problem, so it's a lot to fit into 30 minutes. Which, actually, speaking of, the very first top-rated question is, do you have a published paper or preprint on this system?
I believe, it's a published FDG paper. I don't know if the proceedings are out yet, but it's not on archive. I could send me an email if you're interested in it. Send me an email, but it will be in FDG 2022. I do not believe that proceedings are published yet, but it's part of that proceedings.
All right, so coming soon.
Yeah.
And then we have a very specific question. I am mostly just going to read and hope that you totally understand it. Are all ERA graphs leniency versus linearity, and why are these qualities to focus on?
They are not. So that's sort of what I meant by metrics. You can essentially use whatever metrics you deem necessary or deem useful to you in a design context, right? So you can use number of rooms and number of enemies. You can use whatever, how many arms does my enemy have if you're generating enemies, right? Whatever you want. Just leniency and linearity happen to be sort of, I'm going to use the word canonical loosely here, but it's sort of the canonical examples, the quintessential examples, that's a better word, that are used in a lot of papers that do expressive range analysis stuff.
That makes sense. Yeah, I mean, it's funny because I had forgotten that was the terminology for this concept because I've been iterating on it for a while in a AAA space where it's been just less and less academic over time. And so, we work with similar concepts, but our game's a survival crafting game, and so there's a lot of visualization tools I built out there. And in that case, we're looking at things like, how many resources are there, and how are the resources distributed over a spatial map, because we care about where are players finding those resources, and in what kind of quality and quantity and all that kind of thing. So, yeah, domain specific.
Yeah, I imagine this idea is probably popped up in a lot of different domains, but with very different names. But yeah, it's just visualizing your design space, right?
Yeah, which it is selfishly, I am curious, and it's probably something that's not as easy to just off the top of your head. But that idea that there is, there's lots of academic discussions of this. I would be curious if there are any kind of other top ones that you recommend, because I do know in terms of someone who's very into Proc Gen, but Roguelike Conference is probably the only time I intersect with academia. It was Gillian Smith having a chapter in, I think, game design, procedural. That was my one exposure to this. Are there any other kind of good resources to check out?
So generally the PCG book, which is Norshecker et al., that gives you a brief sort of summary of, at that slice of time, the academic work on PCG. There is some talk about expressive range analysis in that book. There's a bunch of this paper by Somerville et al. I could maybe put together a list of papers. I don't have everything off the top of my head, but there's a bunch of papers I think would be useful to read. But definitely that paper by Gillian Smith that was in the presentation, I would say that's sort of the go-to example or go-to resource for learning about expressive range analysis.
Yeah, excellent. No, and yeah, I would love that little packet of additional summer reading.
Mhm.
A
Yeah.
question from Rourke: are there any other types of grammars that you could see, this being used for?
So this is by no means exclusive to graph grammars. In fact, I think I might have hampered myself a little bit by focusing on graph grammars because they're actually a bit more complicated than regular grammars for reasons. But yeah, the idea of just putting some probabilities on your grammar and then learning from examples is you can do the exact same thing with any type of grammar. I don't see any reason why it couldn't be done. And there's more work on, not in this specific context, but there's a lot more work on learning from examples using like context-free grammars that use like strings instead of graphs. And you can leverage that literature if you want to do much more fancy things like actually learning rules instead of probabilities and stuff like that. So it's still like, there's more stuff you could do that I just didn't have time to do. So this is
Yeah,
still research, it's still
yeah,
stuff to do.
yeah.
Yeah.
And I guess I'm curious too if you have any like off the cuff thoughts on. There was a little bit of discussion in chat about just you know you're looking at the quality of certain outputs, and then you're looking at, okay, well, what rules were applied, but then like how much is there a strong relationship between like what you're perceiving as the quality of the outputs and what rules happen to be applied at that point in time, like how have you found kind of exploring that connection in terms of how often that's consistent and how often maybe there's something else going on there that's hard to pick up on?
Yeah, so there are two, in my head, there are two main things, because I think in a very Bayesian way, right? So the first thing is the initial distribution of the artifacts that you're generating that the grammar inherently sort of generates. So what the rules sort of do, right? And then what the quality of the levels that are generated by sort of what the rules sort of encode, and the distribution of the quality of those levels, right? And I would call that sort of the prior, quote unquote. Um, and then there is how these rules are applied, which is sort of the parameterization that you're adjusting with the system. Um, when you're adjusting these probabilities with the system, you tend to not get, you don't change the what levels can be generated, but which ones get generated and how often. And so in the pool of levels that you generated from your original grammar, you basically make sure that the things that fit the criteria that you want are selected more often. And so that's sort of what you're adjusting. But it does not change, you're not learning rules, you're not adjusting what the sort of the actual grammar, what the actual grammar can generate. And that is a double-edged sword. One thing it gives you is that it makes sure that your levels are playable if your grammar is well formed. And the second thing, the downside is that it can't really be more diverse than the original grammar.
Right, right. Cool.
Yeah.
No, that's fantastic. I like that. Very succinct of the trade-offs there. Excellent. I would love to keep talking. I probably will be sending you messages and being like, please send me more references. But
Please do.
yes, time keeps moving on. So thank you very
Thank you
much.
so much.
Yes, it was wonderful to have you.